on challenges in design and construction of underground cut and cover box section of Chennai Metro Phase 2 in Corridor 3, which will be presented by Mr. Chiranjeev Sarkar. As you are aware, the TAI webinar series was started in the month of August 2024, and the first webinar was conducted on the topic of I system, index of ground structure, a comprehensive classification characterization system for ground, rock and soil by Bimnation Hoss, Technical Director and Senior VP of TAI. We saw participation from different organizations, and the objective of this webinar series is to promote and update the industry about the advancements in the tunnel engineering. The idea is to ensure that a webinar is conducted on a monthly basis and knowledge dissemination in the field of tunneling is done on a regular basis. Now, I also take this opportunity to welcome today's speaker, Shri Chiranjeev Sarkar, Principal Engineer at GeoConsult India Private Limited. He is also the member of Governing Council of TAI. Welcome, sir. I hope we shall have a knowledge enriching session today with all the participants. I wish all the best to each one of you. Before Mr. Sarkar gives his webinar, may I request each member to introduce himself so that we know that other participants, who are the other participants.
Sir, this side R.K. Singh.
Thank you, sir. Thank you.
Okay, sir. Okay, sir. Right, sir.
Next. Sir, introduce yourself.
Mr. Ankur Soni.
Yeah, carry on, sir. Carry on, please. Carry on.
Mr. Ankur Soni, can you please introduce yourself, sir?
Hello.
Mr. Arunil Paul. Sir, can you please introduce yourself if you can hear us?
हाँ किया है अभी तो मैं ऑफिस में हूँ मैडम कुछ मीटिंग में है वो थोड़ी देर बात करेंगे 1 घंटे बाद
सर Sir, next participant, Mr. Arnab Sur. Sir, can you please introduce yourself to the all the members?
Yes, I am Arnab Sur. I am the head of department of structure and geotech at Aisha India Private Limited.
Good. Next.
Shri Chandra Shekhar, sir, can you please introduce yourself, sir? Chandrasekhar, sir, can you hear us? Next participants, Mr. Datta Binar. Sir, can you please introduce yourself?
Myself, Datta Binar, Senior DJ, Mumbai Metro Rail Corporation.
Thank you, sir. Thank you, sir. Mr. Deva R. TSM, sir, can you please introduce yourself? Mr. Dr. Kanu Priya, ma'am, can you please introduce yourself?
Hi, I'm Dr. Kanupriya. I work as the Associate Director in Penny, India, which was originally Geodata. And so we mainly work in infrastructure projects in our organization. So roads, rails, metros. Yeah, that's
Okay,
about it.
thank you.
My main background has been in hydropower, although mostly. But I have
Thank you.
been
Thank you.
working for undergrounds and tunnels.
Thank you. Welcome.
Thank you.
Mr. Harpal Singh, sir, can you please introduce yourself? Next.
Hello, myself Dr. Harpal Singh. I am Principal SSIIT Gurdaspur.
Okay, sir. Thank you, sir. Welcome. Mr. Kalikleti Michael Paul. Can you please introduce yourself, sir, please?
Yeah, hi, sir. Good evening. This is Michael Paul. I'm from GeoConsult India. I'm a senior structural engineer currently working with GCI and have good experience in Chennai Metro and Calcutta Metro and various projects in India. basically in structures in underground and metro tunneling.
Thank you. Thank you, sir. Thank you, sir. Mr. Sharik Khan, sir, can you please introduce yourself?
Yeah, good afternoon. I'm Sharik Khan, working as a senior design manager in Atkins. In Gurgaon. I'm working in the infrastructure tunneling and transport tunneling department. Yeah, that's it. Thank you.
Thank you, sir. Shri Krishnendu Chaudhary, sir, can you please introduce yourself, sir?
Yeah, good evening. I am Krishnendu Chaudhary, working in GeoConsult India currently as a senior structural engineer.
Okay, thank you, sir. Mr. Mayank Thakur, sir, can you please introduce yourself?
So my name is Mayank Thakur. I'm working in GeoConsult India as an engineer, geotechnical.
Thank you, sir. Mr. P.S. Sengupta, sir, can you please introduce yourself? Okay. Mr. Ramshid Padusha, can you please introduce yourself, sir?
Good evening, everyone. My name is Ramshid Padusha. I am working as Superintendent Engineering, Ministry of Road Transport and Highways, North, Government of India.
Welcome. Welcome. Mr. Ram Swarup Khileri, sir, can you please introduce yourself? Ram Swarup, sir, can you please introduce yourself? Mr. Ravi Sharma, can you please introduce yourself, sir?
Good evening, everyone. Myself, Ravi Sharma, currently working as a junior structural engineer at GeoConsult India Private Limited.
Thank you, sir. Shri Raymond Chan, sir, can you please introduce yourself, sir?
Good evening. Can you hear me?
Yeah, yes.
Good evening. I'm Raymond Chan from Hong Kong, from one of the company called Polar Construction Limited. I'm a technical manager, mainly working for geotechnical work. Yeah.
Thank you, sir. Welcome. Mr. Sandeep Singh, sir, can you please introduce, sir?
Hi, good evening, everyone. This is Sandeep from Jindal Stainless, and I'm taking care of this business strategy and this tunneling infra as well. I'm also a general council member of this Tunneling Association of India. Thank you.
Welcome, Sandeep.
Thank you, sir.
Mr. Sanyam Tyagi, sir, can you please introduce yourself, sir? Mr. Sarath Chandran, can you please introduce yourself, sir? Mr. Shivansh Tandon, sir, can you please introduce yourself?
Yeah, good evening, everyone. Shivansh Tandon this side. I'm currently graduating from an engineer college itself.
Okay. Thank you. Sharath, sir, can you hear us? Sharath Chandran, sir, if you want to introduce yourself.
Hi all, my name is Sharath Chandran. I'm a senior tunnel design engineer in Shivashakti Engineers and Consultant. Thank you.
Thank you, sir. Mr. Sonu Anand, sir, can you please introduce yourself?
Hello everyone, I'm Sonu Anand and I'm currently working as structural engineer at Amberg Engineering.
Thank you, sir. Welcome. Mr. Chirag Upadhyay, sir, can you please introduce yourself?
Yeah, hi all. Good afternoon. I am Chirag Upadhyay and I am a graduate tunnel engineer in Atkins Realis. I sit in Bangalore office. Yeah, thank you.
Thank you. Welcome. Mr. Vibhav Vishal Pandey, sir, can you please introduce yourself?
Hello, sir. I am Vishal Pandey. I am currently working in Pune, India, and I am junior engineer here.
Thank you, sir. Welcome. Mr. Venkata Gundoju, can you, sir, please introduce yourself?
Hello all. Good evening. My name is Venkat Raghavendra Kumar Kundoju. I'm working as in a high-speed rail project in London. in the tunnels department, and I have around 11 years of experience in tunneling. Chennai Metro Rail project, Lucknow, Mumbai, and Qatar as well. Thank you very much.
Vikas, thank you, sir. Welcome. Mr. Vikas Singh, sir, can you please introduce yourself? Mr. Vipin Bihari, sir, can you please introduce yourself?
Yes, good evening, sir. I'm Vipin Bihari. Currently I'm working as a geotechnical design engineer. Pini India. Hello, I am audible.
Yes, yes.
Yes. So my name is Vipin. I am working as a geotech design engineer in Pini India.
Okay, thank you.
Thank you,
Now we
sir.
will begin the presentation. Thank you all. Welcome to this webinar series.
First you introduce.
Sir. I would like to thank our Secretary General, sir, and Secretary CBIP, Shri Enke Dinkar, sir, who is chairing the session today on webinar, and also Shri KK Singh, sir, Treasurer TAI and Director WR CBIP for their presence in today's webinar, and Shri SK Batra, sir, Consultant Energy CBIP, to be present in this webinar. We also have with us other members of CBIP, Shri Bismay Swan and Shri Ravindra from IT team, who are attending this seminar or this webinar. So I welcome all of you in this second webinar of TI. And before we begin the TI webinar, I just want to introduce Mr. Chiranjeev Sarkar, who is also a GC member of TI. Mr. Sarkar is a postgraduate civil engineer with 15 years of extensive experience in detailed design and design management, geotechnical investigation, execution planning for metro, railway, road and bridge projects. His contributions span metro projects in 8 major cities across India. Mr. Sarkar is a principal engineer at GeoConsult India and leads significant tunnel and underground projects both domestically and internationally. He is serving as a principal designer for the Mumbai-Ahmedabad High-Speed Rail Package C2, Jaipur Metro, and NFL Tunnel T1, T112, and many more. Mr. Sarkar has practical achievements. He has presented and published over 12 papers at prestigious national and international forums. His excellence in tunneling has earned him several accolades, including being a finalist in Young Tunneling of the Year at the ITA Award 2021, as well as receiving the Industry Expert National Award 2020 and the Research Excellence Award 2020. Mr. Sarkar does participate in professional organization and serving as executive committee member of the Kolkata chapter of the IGS, which is the Indian Geotechnical Society, and the Indian Society of Earthquake Technology, and he's also a GC member of TEI. We welcome Mr. Sarkar in this webinar and thank him for his time today. He'll begin the presentation, the second webinar of TI, on the topic of challenges in design and construction of underground cut and cover box stations of Chennai Metro Phase 2 in Corridor 3. We welcome you, sir, and thank you once again, and you may begin your presentations.
Thank you, Akshay. Welcome to all. Am I audible? Just for again sound check.
Yes, you're audible. Can you please make your presentation in PPT mode?
Slide mode.
Yes. Slide mode. Slide share.
I would request all to just switch off your camera for better connectivity and for better watching of this presentation. I am also switching off my camera. Is it visible, Akshayji?
Yes, sir. It is visible. You may begin the presentation.
Yes, visible. Please proceed. Yes.
Okay, sir. Okay. Just I'm going for full screen mode. Okay. I hope it is visible. Good afternoon, everybody. Today I'm going to share my experience in the design of tunnel and underground structure for metro projects. So, topic of my today's presentation is challenges in the design and construction of underground cut and cover box station of Chennai Metro Phase 2 Corridor 3. So, about myself, I'm Chiranjeev Sarkar, Principal Engineer of GeoConsult India Private Limited, also governing council member of TAI. So about GeoConsultant is an engineering consultancy group of various disciplines like civil, structural, and geotechnical engineering, soil, rock mechanics, geology, environmental and mining engineering, and electrical engineering. We have offices in Argentina, Austria, Brazil, Colombia, Chile, Germany, India, Peru, Singapore, Slovak Republic, and Turkey. So these are the pages of GeoConsultant in the Europe, in the Americas, and in the Asia. So now I'm moving back to my main technical presentation. So there are these are the content of my today's presentation. It include general overview, location, and geology of the Chennai Metro Phase 2 Corridor 3, various type of challenges, features of Chennai Metro Phase 2 Corridor 3. In today's presentation, I will discuss about three major challenges as the three case study. Case study one, there is a first challenges features will be, our first case study is the design and construction of the UG station at mixed ground condition. The second case study, that is the case study two, design and construction of intersecting interchange station laying at mixed ground. And the third case study is the design of an underground station supporting entire flyover and ramp. So current slide is showing Chennai Metro Phase 2 Corridor 3 in purple color line. I think you can see. So it includes 29 underground station and 20-kilometer associated tunnel. Entire Corridor 3 has been subdivided into 5 contact packages, that is UG1, UG2, UG3, UG4, and UG5. So about the geology of the entire city is classified into 3 region-based geology, like sandy area found along the river bank and coastal, clay area mostly covering the city, and hard rock area found in the some central and the south part of the city. So Chennai Metro Phase 2 Corridor 3 contains various challenging features like underground station at mixed ground condition, means half of the station situated in the soil and half of the station situated in the rock. So that is called a mixed ground condition. Then intersecting interchange station laying at mixed ground. So it's an interchange between the corridor 3 and corridor 4 line. You can see that is the intersecting interchange, and it is also situated in a mixed ground condition. That half of the station situated in the soil and half of the station laying the rock. Then flyover running along the length of the station. You can see that the station is supporting entire flyover and ramp. And the fourth one is the UG station having crossover and 2 level of parking. So among these challenges features, today I will discuss about first 3 challenges as a 3 case study. Case study 1, case study 2, case study 3. So now I will directly move to the case study 1, that is the design and construction of the UG station at mixed ground condition. So I would like to know, am I audible properly and my screen is visible properly? Is there any obstacle, sir? Everything is fine? Can I proceed?
Yes.
Okay, thank you, sir. Thank you for confirmation. So these are the some major salient features of the case study 1 presentation, the geotechnical condition of the case study 1 presentation, which was chosen for the Tiruvallur metro station. Then the description of the station, then the model of the case study, construction stage analysis, service stage analysis, stability analysis, discussion on the analysis and the result, conclusion, and a few references. So, design and construction of the Tiruvallur underground metro station of Chennai Metro Phase 2 Corridor 3 has been chosen here as a project-specific case study. Tiruvallur UG station belongs to contact package UG5. Current slide is showing borehole location is marked into the station layout. Based on borehole location, geotechnical long profile has been further plotted, and you can see that the further station box has been superimposed into the geotechnical long profile. And now you can see from the rock line diagram, this is the rock line diagram. So half of the station situated in the soil and half of the situated in the rock. And this is the tunnel profile actually. This is the tunnel profile. So this is the station box, long section of the station. So Current slide showing the station geometry for the Thiruvanmiyar UG station. Length of the station is 152 meter, height is 16.5 meter, width of the station varies from 20.35 meter at the middle and 24.5 meter at the end, that is in the shaft location. So as I already told in the previous slide, that the half of the station is situated in the soil and half of the station is situated in the rock. So due to difficulty in the digging in harsh data as well as due to self-standing nature of the rock, the wall has been proposed here is to be terminated above the base level. You can see that the wall is terminated above the base level with the help of the shear pin that is called toe pin. So during excavation stage, toe pin has been provided as a to provide the adequate stability to that diaphragm wall. After excavation and the casting of base slab, a 1.2 meter thick stitch wall has been provided as a connection between the diaphragm wall and the base slab. This connection will provide the rigid box behavior of the structure. So, due to varying rock layer along the station element, this three case has been adopted as a part of the model of the project-specific case study. Two pin is required for case 2 and 2B. That is the first one is the case 1, that is the diaphragm wall terminate at least 3 meters below the base layer. This is the conventional normal metro station actually, that having diaphragm wall and diaphragm wall having some embedment length which is beyond the base layer. That is called the case 1. And we don't know the actual level of the starting level of the rock wall. So there is 3 probable cases may arise. There is case 1. Then case 2, if my rock encounter above the base level. So there it is also further subdivided in 2 parts. That is the case 2A. Rock layer, if it is more than 3 meters below the concourse slab, that is called the case 2A. And if my rock is the within the 3 meters below the concourse slab, so that is called case 2A and 2B. So shear pin is required for both case 2A and 2B. Current slide showing the diaphragm wall with toe pin embedded into the, you can see diaphragm wall with toe pin embedded into the rock layer to provide the adequate embedment to the diaphragm wall. So due to the presence of the hard rock layer, diaphragm wall trenching is stuck up and the project suffered badly. And that time, the structural steel member are used as an innovative and economic engineering solution. So, starting this is the zoom view of this part, the section, the detailed one. You can see that this is starting level of the rock layer. Say example. So, due to presence of the hard rock layer, the trenching is stuck up and project suffer badly. So that time, toe pin, that is shear pin, used to provide below the diaphragm wall that provide the adequate embedment to the diaphragm wall. So this time steel structural member are used as a innovative economical solution. So here there is some utilization of the structural steel member in the design of the underground structure. So now present slide showing the diaphragm wall in the rock system. In the plan you can see this is the plan. This is the plan. This is the cross section of the diaphragm. This is the elevation, and this is the cross section of the diaphragm wall, showing the structural steel member is inserted into the diaphragm wall. These are detailed. The structural steel member. This is the structural steel member is inserted in the diaphragm wall through a 250 mm dia pipe, and it is embedded into the rock layer through drill hole. So into the embedded rock layer through the drill hole. Then the gap between the tube is and the member is filled with the grade 40 non-shrink grout material. Further, Fisher grout is also provided for rock for excellent bonding. So now I will directly move to the advantage part of this D-wall with the two-pin system. First one is the no requirement of separate time and activity for temporary earth retaining structure arrangement, as the top-down construction sequence with the diaphragm has been chosen here. Second, no requirement of the separate traffic decking With the top-down construction, it can be easily managed. After the casting of the roof slab, traffic can be diverted above the roof slab. Then there is the reduction of the in between of the diaphragm wall, as we are not casting full height of the diaphragm wall. Of course, there is some limitation. That is the it's required more skilled manpower and the equipments. So these are limitation. Of course, there is as a part of the advantage, there is a major quantity save of the temporary architectural structure. It's a fastest construction with the less manpower. So these are the advantages. The only limitation is that it's required the more skilled manpower and the equipments. So as a part of the construction stage analysis, entire construction stage analysis has done in the Plaxis software. Toe pin is assigned into the model as a spring stiffness of the equivalent to the member property. So you can see that this is the initial stage. Then this is the diaphragm installation stage. Then the station excavation. Then entrance excavation. Then the backfilling stage. Then the service condition. So all these stages has been done in the for top-down sequences. So, as a part of the service stage analysis, the service stage analysis has been done in the STATCO software for both case 2A to B. Here, stitch wall has been modeled as a enlarged section. You can see as the enlarged section. The envelope of the all cases, case 2A to B normal cases, has been considered during the RC detailed design of the diaphragm wall and the stitch wall. As a part of the stability analysis, entire station box has been checked against toe stability, which is done in the Plaxis 2D software. Factor of safety for the toe stability has been found within a limiting value. Ground stability also been ensured by checking the ground surface settlement with respect to its limiting value. Also, we have checked the horizontal deflection of the diaphragm wall for different stages of excavation. What are the horizontal deformation of the diaphragm that has been also been checked. So now you can see that the bending moment and the shear force of the diaphragm wall here. These are the bending moment, this is the shear force. And structural RC detailed design has been done based on this envelope diagram. Further, structural steel check for the toe pin has been done in line as per the criteria of IS 800 2007. So now I will move to the conclusion part for the project specific case study one, that is unconventional and innovative technical solution may save projects many times for its long deadlock conditions. You can see that due to the presence of the hard rock layer, our trenching and the gabbing can be stuck up. And but as a innovative solution, still toe pin member has been assigned. So structural design of the three-way station, which fall into the mixed ground condition of the Chennai Metro Phase 3, is referred here due to difficulty in the excavating hard rock strata and arrangement of the shallow diaphragm wall terminated above base level with the shear pin embedded into the rock strata has been adopted. So this arrangement basically reduce the requirement of any kind of temporary architectural structure, because here D wall is behave like a main body of the structure and also a retaining structure. So it's this arrangement reduce the requirement of any kind of temporary architectural structure like soldier piles, sickle piles, etc. So therefore, it's help by saving time, manpower, material cost of the temporary and activity for this temporary architectural support. Entire sequence of the construction has been analyzed in the finite element based numerical software for checking the structural design stability. Of course, structural stability and the safety of the adjacent structure was the most priority during the entire life of the design. These are the few references which has been used or during the design of the Thiruvanmiyur station. Also, I would acknowledge the support from the entire team involved in the Chennai Metro Railway project. That is the design firm, GC, then client, the support from entire site. So, just for information, the present case study has been already published in Indian Geotechnical Conference IGC 2021. Now I'll move to the second challenges features, or I can say case study 2. That is the design and construction of the intersecting interchange station lying in the mixed ground condition. So these are the major salient features for the case study presentation 2. Design and construction of the Thirumaila station of Chennai Metro Corridor 3 has been chosen here as a project specific case study 2. Thirumaila station, you can see, is an interchange of corridor 3 that marking the yellow line, and corridor 4 that marking the yellow line, and corridor 3 that marking the purple line. So it's an interchange station, Thirumaila station. So entire Three Mile station has been subdivided into mainly two parts. That is, which is the island station along the corridor 4, that is C4, and the Stark station along the corridor 3. So due to site constraint, you can see that the width of the station is very narrow here. Due to site constraint, width of the corridor 3 part of the station has been kept narrow, and which result the stacking of upline and downline. So since the station width is very less, so therefore there is a stacking of upline and the downline. So corridor 4 part of the station is proposed as an island between the upline and downline. So what has been done? This is the stack station. So upline, there is a upline and downline. So in the corridor 3, so corridor 4 part of the station has been proposed as an island between the upline and the downline. I will show in detail in the next slide as a 3D isometric view. Here, just station layout of the interchange station has been shown here. So you can see the three-dimensional view of the entire station box of the three-dimensional station along with the intersection area. So you can see that this is the narrow station having the upline and downline. So and the corridor 4 tunnel is going in between this upline and downline. So you can see from here. In the left hand side, that is the cross section area of the corridor 3 station with the interchange, and the right hand side with the stacking. So you can see this is the corridor 3 having single track in a floor. This is the upline, this is the downline, and corridor 4 part of the station is going in between as an interchange. So, as I told earlier, the geological condition of the Chennai city is mostly clay, sand found along the river bed and the coastal area, and hard rock found in the some central part and the south part of the city. So, for 3 Mile station, subsurface stratum at the site contain mostly cohesionless soil and weather rock. Current slide is showing the depth-wise geotechnical parameter for 3 Mile station. Also, further station box has been superimposed into the geotechnical long profile again for 3 Mile station. You can see from the rockline diagram, that is the it is the rockline. This is the half of the station situated in the rock and half of the station is in the soil. So this is the rockline diagram. So geotechnical profile with the superimposed station box. This is the island part of the station. That is the station which is parallel to the corridor 4, that is the island part of the station, and this is the geotechnical long profile superimposed for the stack part of the station. So model of the case study. Due to varying rock layer along the station alignment. Two cases has been adopted as a part of the model of the project's case study. That is the case 1 and case 2. In case 1, rock layer at below or at island undercup level base slab. So diaphragm here with a typical embedment of the 3 meter, you can see into the grade 4 of the beta rock uh, and 5 meter for the grade 5 rock. That is the condition of the case 1. In case 2, rock layer below the island undercup level, that is the case here, diaphragmal terminated above the undercup level, and since the diaphragm terminated above the undercup level, so toe pin embedded into the rock strata is required for both for case 2, and case 2 is applicable specially for the stack 3 station, that is basically from the GL grid 16 to GL grid 18. Okay, then now current slide showing the cross section with the case 1 condition, that is and also 3D cross sectional view of the you can see it's a typical case 1 condition, dual having embedment below the undercup level. Then in the also you can see the same in the 3D cross sectional view, that is for the island 4 part of the corridor 4 part of the island station. Now case 2 condition, and that is the with the case 2 condition, and also the stack part of the stack part, you can see the up line and the down line, and island part having, that is the interference part. So current slide showing the different stages of construction sequence of top down sequence for both case 1 and 2 conditions with the entrance that is model in the placis. Current slide showing the different construction sequence of the island. This part is basically this defined construction sequence of the island part of the station with the case 1, which is applicable for the corridor 4 part, that is the grid 1 to 18 of the station, that with the case 1. And the second slide shows the different construction stages for the narrow stack part of the station with the case 2 condition. Since the narrow part having the relatively higher depth, and here case 2 condition prevail. So here shear pin toe pin has been assigned as a spring stiffness of the equivalent member property. Entire service stage analysis has been done in the StatPro software for both case 1 and case 2. That is, case 1 mean island part of the station, and this is the case 1, and case 2 is the stack part of the station. Stitch wall has been modeled again the similar way. Stitch wall has been modeled as a uh, as an enlarged section. Stitch wall has been modeled as an enlarged section. So envelope of the all these cases has been considered during the detailed design of the diaphragm wall and the stitch wall. All different level of the slab has been checked by developing the 3-dimensional plate model with a permanent opening. You can see here also the slab has been modeled with a plate with a permanent opening, which is subject to full service load state under the both serviceability check and an ultimate check for the limit state, that is ULS and SLS condition. Of course, stability of the entire station has been checked against the true stability in Plaxis 2D software for both island part of the station and stack part of the station. Factor of safety for true stability have been found within a limit. Ground stability also has been checked for the entire excavation and construction has been performed in the Plaxis 2D software. Ground stability also be ensured by the checking the surface settlement with respect to its limiting value. It is also found within limit. So as a outcome of the different series of the model analysis for both uh, island part and the stack part of the station, deformation, shape, bending moment behavior also has been studied. So current slide, you can see that the horizontal deflection of the diaphragm wall has been checked for different stages of the excavation for both island part of the station and stack part of the station. Current slide also showing the bending moment envelope diagram for both part. That is the for excavation, backfill, service connection, all cases. It's the envelope of the all cases for both island part of the station, the left hand side and the right hand side in the stack part of the station. The similar way structural steel design because in the case 2 you have the 2 pin shear pin, so structural design check for that shear pin with respect to the loading condition uh, for both case 2 the stack part of the station has been checked in the steel code IS 800 2007. So now we'll move to the conclusion of the project-specific case study 2. Of course, due to site constraint and the land issue, as I already shown, the corridor 3 part of the station is adopted is a narrow width stack station. Thus, corridor 4 part of the station is proposed as an island between the stacking of upline and the downline with a intersection connection area. So this is the basic geometrical features of the entire 3 mile station. It's an interchange station having stack of upline and downline because of corridor 3 is a very narrow width due to land issue, and the corridor 4 part of the station is proposed as an island station between the stacking of upline and downline. So of course, as a part of the economical approach in the design and construction, 3 mile station has been proposed with the top-down method to get the advantage of the diaphragm wall as faster construction, less manpower and equipments. Of course, due to encounter of the hard rock layer, shallow deep diaphragm wall with topin embedded into the rock strata system has been adopted. Further stitch wall has been provided as a connection between base slab with the diaphragm wall. The major challenges were faced due to the unsymmetrical and irregular shape of the station box at different level, and also its interchange connection area uncertainty of the rock profile, which occurred basically complex behavior of the station geometry under various loading conditions. So definitely structural stability check and safety check was also a challenge, and it has been ensured by checking its limiting value each and every stage of the design analysis. So these are the conclusions. These are the few references which has been used during design of this station. And of course, again, presenter acknowledged the support from the entire team involved in the Chennai Metro Railway project. So, just for information, the present case study also been published in 9th Civil Engineering Conference in Asian Region, Session 9. So now, last one. I just quickly gone through the it's a project specific case study 3. That is a design. I just quickly gone through because there is a very short of time. So, there is a design of underground station supporting a flyover and ramp. So, to provide the multi-dimensional transportation system for a busy road crossing at Radhakrishna Salai Junction station of the Chennai Metro, a highway flyover is planned above the underground corridor station. So, design and construction of the Radhakrishna Salai Junction station from Chennai Metro Phase 2 Corridor 3 has been referred here as a project-specific case study 3. In the next slide, I will show some three-dimensional view and the cross-section design along with some designs. As a description of the design of the underground station supporting flyover ramp, the entire station comprised of 3-level slabs supported in the 2 diaphragm. In the metro station, we already know that there are 3 levels of the slab. That is roof slab, intermediate slab, that is called concourse slab, and the base slab. So entire station is supported by 3 level of the slabs and the both sides the diaphragm wall. So here diaphragm wall as a considered as the external wall member forming the station part. So both main station and the launching shaft area is proposed here as a top-down sequence of construction to get the advantage of the diaphragm wall and the decking. In addition, there is a flyover running along the station, which is supported on the roof slab. So the entire station box will behave like a foundation of the foundation of the entire flyover and the ramp part. So you can see that these are the flyover part and this is the ramp part of the that is supported on the supported by the station box. So this is the long sectional view of the Radhakrishnan Chalai Junction station. This is 3D isometric view. This is a long section view. So these are the flyover. You can see the flyover pier also, and these are ramp part. So flyover pier there is a actually supporting by roof slab having some cross beam. Again, I will show that some 3D isometric view along the length of the station. This is the flyover part, this is the ramp part. And next slide, you can see that the long sectional view. So this is a long section view of the station along with the flyover. This is the 3 level of the slab. That is the roof slab, concourse slab, and the base slab. The tunnel also. This is a platform, the concourse area. And you can see that there are some cross beam is there in the roof level. So cross beam actually supporting this flyover here. So this is the 3D cross-sectional view you can see. In the earlier slide, I have shown the long section view. This is a cross-sectional view. This is the flyover. Now I will move to the design part. The structural design here considered as a critical forces from the construction analysis, which obtained from the soil structure analysis, which is done in the Plaxi software. Of course, PR, there is a two type of flyover PR. There is a 20-meter 20 plus 20-meter long flyover span supported pier is supported on the station. You can see here the 3 meter by 2.5 meter wide long roof beam is supported on 1 meter diaphragm. So there is a roof level beam also here. And there is a pier at the end location that is 35 meter by 20 meter span. But one side span is 30 meter, 35 meter, another one side is a 20 meter. And there is some typical span is there in the 20 meter plus 20 meter span. So all flyover pier are supported by beams, which is monolithically connected with the roof slab. The beam size is 3 meter wide and 2.4 meter is depth, which is directly supported on the diaphragm on the both sides. Of course, there is analysis for the flyover part. So below table shows the all possible load has the flyover span. The design summary of the forces. These are the summary forces for 20 meter flyover span, and this is a 35 meter by 20 meter flyover span. In here you can see that the load has been assigned to the both 2D frame and the 3D roof level plate model also. The we have done both 2D and 3D analysis. Here just a typical 2D frame with the flyover load has been applied, and just on the right hand side you can see the bending moment behavior also. So accordingly, we have designed the structural element. Of course, there are 3D model also done. Based on that, the slabs also designed. So, and based on the envelope course, we have designed this RC detail design for the roof slab and other component of the station box. So now I will move to the conclusion part. The major thing is underground construction are gaining popularity by playing a key role in improving many more urban spaces congestion problem. Of course, the underground construction are gaining popularity nowadays because of its contribution in the urban space congestion problem to resolve this urban space congestion problem. So to provide the multi-dimensional transportation system on a busy road crossing, rather at Radhakrishnan Junction Station, a entire flyover is planned above the underground corridor station. So these are these main features of the case study 3. The present case study describes the design concept, optimization opportunity, and the challenges of this underground station supporting a flyover ramp. So entire station comprising 3 levels of the slab supporting 2 diaphragm wall, and diaphragm wall are considered as the external wall which with the slab forming a part of the internal framing. Entire underground station construction is planned with the top-down sequence. Flyover and the ramp part has been planned to cast later on. Once the civil work of the underground station completed, then the flyover and the ramp work will be done. Of course, the one most important structural stability and the safety of the entire area has been ensured in each and every stage of the analysis and the design. So this case study also another process of the publication. It's not yet till published till date, so that's why I'm not referring here. But it's also this case study also is possible. Now I will just show few site pictures during the live project, the Chennai Metro Phase 2 Quarter 3. So these are the few site pictures that the execution is already started and going on. So it's already 4:56, I think. Thank you again, all. So these are our some references. You can connect TAI through our LinkedIn, blogs, YouTube, and TAI website. Just take a screenshot of that. You can scan from your mobile, and then you can directly connect to us. So I would also request all to be a part of Tunnel Association India, since I belongs to a GC member of Tunnel Association India, also past vice chair of Tunnel Association member, young member group. So I would request all of you to get touch with us to please renew your membership, and also those who have not yet taken your membership, please become a member. These are Google form. Just take the snapshot of this, and later on you can just scan this form, and directly you can fill up our Google Form, and you can get our membership, and you can take all the benefits of the time. Thank you again. Bye. Akshaji, over to you.
Thank you, sir, for your time. Now I want anyone to ask question to Chiranjeev, sir. Anyone wants to ask question to Chiranjeev, sir? Please unmute yourself and ask question to Chiranjeev, sir.
Yes, am I audible?
Yeah. Yes, sir.
Yeah, good evening, everyone, again. So I was actually, you mentioned about the varied rock layers in the formation of tunnels and underground structures, right? So also there is an existence of certain shear areas in these tunnels. So while going through some research papers, I actually found out like that stainless steel is a material that can be used to, form structural components or electrical components so as to provide better corrosion resistance or like higher durability and strength, especially for the shear zones. So can I get some opinions about the same?
I think yes, it's time to think about the option of the stainless steel, because this practice already adopted in the entire world, and we are almost 20-30 years lagging behind of them. Definitely we have to think about, but there is no I think only because of some maybe tender and other obligation people are not using. Maybe that item is not mentioned in their BOQ item in the tender during the tender time, which has been prepared long back as per the earlier conventional method like that. So that's why maybe people are not using. But of course, I believe that yes, it will be very effective solution to using as a stainless steel, and people should think about the adopting of the stainless steel. At least whatever has been done in the past, but we can improve in our future. No?
All right, sir. Thank you so much, sir.
Yes, thank you everyone for your time and attending this webinar. We hope to meet you again in the next webinar. Okay, thank you, sir. Thank you all.
Thank you.
Thank you.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.
Oh, thank you. Thank you. Thank you, sir.
Thank you, Chiranjeevi. Wonderful. The session was entirely informative. I know coming up with these new ideas. So wonderful explained and everything was properly mentioned.
Thank you, sir.
Thank you, Sirji. Thank you. Thank you.